Welcome back, everybody, to another week of Computer Science 150. Uh, this week, we're going to be following a pattern very similar to what we did last week, in that today's lecture is going to be focused exclusively on the lab exercise that we're doing this week. And then we will run the lab as usual this week on Tuesday and Thursday. The difference between this week's lab and last week's lab is that this week's lab, as has been our pattern for most of the term, will be graded. So you'll be completing your work and turning it in to be graded, unlike the optional lab that we had last week. All right, and once again, in this week's lab, we're going to be implementing an algorithm to solve a particular problem. Uh, One difference this time around is that in last week's lab, I gave you quite a bit of code to get you started. For this week's lab, I'm going to be giving you considerably less code to get started, and it'll be more on you to go ahead and write all the necessary code for the lab exercise. But the trade-off is that I think and I hope that this week's lab problem is going to be a little bit simpler and a little bit easier than last week's lab problem. All right, so let me begin by taking you through the purpose of this week's lab exercise. As usual, when you start the lab, the first thing that you're going to do is download a project that I'm going to provide, and here is the project that you'll be downloading. And the first thing that's important in this project is a text file. One of the files in the project folder is this file, points.txt. And what you'll find in this file is a list of coordinates for a group of 40 points that live on a two-dimensional plane. Right, so each of these lines is a combination of an x coordinate and a y coordinate for a point somewhere in the plane. These points appear in no particular order, and they're scattered all over the plane. Right, now, what we're going to be doing in this week's lab exercise is we're going to be computing something from this set of points. And specifically, what we're going to be computing is a set of boundary points for this collection of points. Right, so in the picture here, here's a visual representation of that set of points scattered around the plane, and also a visual representation of what we're going to try to do. What we're going to try to do is we're going to try to compute the boundary points in this collection of points. And in this picture, you see them basically connected together to make a curve that goes all the way around the points. And that's going to be the main work that you're going to be doing in this week's lab exercise. Essentially, what you're going to be doing is you're going to be writing an algorithm that will read my original collection of points. From that original collection of points, you'll compute a set of boundary points that you can use to make the curve that wraps around the points. And then you're going to save a list of those boundary points to a second text file. All right, then also in the project that I'm providing for you, I've also provided some code, and what that code is designed to do is when you run it, is it will launch an application that will show you a graphical display of both the original set of points and also the boundary curve that you created in the algorithm that we're going to do. All right, and once both the original list of points and the list of boundary points is available in the project, you will then be able to run the visualization program, and it will show you a picture of both the points and your boundary curve. And at that point, you'll be able to judge whether or not you did the right job in constructing the curve. What you're looking for is something that will end up looking like this. Okay, but to get to that point, we need to describe an algorithm that you can use to actually locate and find the boundary points that we're looking for. And that's what I'm going to be spending the next few minutes talking about. I'm going to walk you through the details of the algorithm that we're going to end up using in preparation for you actually implementing this algorithm in the lab exercise this week. Okay, so next, what we're going to do is we're going to take a look at some of the elements of this algorithm that are going to be necessary to compute the boundary curve that we're looking for. All right, the first concept that we're going to deal with is the concept of what's known as a polar angle. And here's a representation of this concept. For this concept to make sense, what you will need to work with is pairs of points. So in the picture here, we have 2 points. At this end, we have a point P, and at the other end, we have a point Q. And these 2 points are playing slightly different roles in the picture. The point P is what's known as a reference point. You can sort of think of it as being something like the origin in a coordinate system that we are laying down in the plane. And then what we're going to be doing is describing the location of other points relative to that reference point. So in the picture here, we also have a second point Q. And what we're going to be doing is describing the location of that point Q relative to the reference point P. All right, now specifically what we're looking for here is a way of describing where this point Q is located relative to P. And part of this description involves an angle. It's called a polar angle. And the angle is the angle that you get if you drew a line from the reference point to the other point, and then just measured the angle between that line and the x-axis in the coordinate system, right? So that gives you an angle theta that shows up right here in the picture. And that is the angle we're going to be working with. It's called a polar angle. Right now, one thing you'll need to know to do this week's lab exercise is how to actually compute that polar angle from the 2 points that you're given, the reference point and the other point. Right? Well, the procedure for doing that is to begin by computing the differences in x and y values between these 2 points. So for example, if you take the difference in the x coordinates of these 2 points, that gives you a measure called delta x. And if you take a difference in the y coordinates of these 2 points, the y coordinate of this one minus the y coordinate of that one, that gives you a second distance called delta y. All right, and then using those 2 distances, you can plug those 2 distances into a mathematical function called the atan2 function. And what that function will return to you is the angle that you're looking for, and it will give you that angle in radians. All right, and it turns out that there is an atan2 function in Java. It's called math.atan2, and that is the function that you'll be using to compute these polar angles whenever it becomes necessary to do so. All right, so this is going to be one of the foundational concepts that we'll be using in this week's lab. All right, now another foundational concept that we're going to be using is a concept that can be applied to groups of points. Specifically, one of the things that we're going to be doing in the algorithm is we're going to be looking at groups of points 3 at a time. And here are a couple of pictures of the kinds of things you can see when you look at groups of 3 points at a time. All right, so in each case, we're going to have 3 points, P, Q, and R. And we're going to connect these points together to make a pair of line segments. One goes from P to Q, and the other one goes from Q to R. Right. Now, the interesting question that we'd like to ask whenever we have a group of 3 points like this is what happens as you're rounding the curve going around Q headed toward R? As you pass Q, are you making a left-hand turn or are you making a right-hand turn? Right, so in the first picture here, we have a picture of 3 points, and in this picture, as you pass Q, you have to make a left-hand turn to head off toward R. And in the second picture, as you pass Q, you actually have to make a right-hand turn as you head off toward R. And this is going to be a key distinction for us. Whenever we have groups of 3 points like this, we'll want to know whether the turn that we have to make in the middle is a right-hand turn or a left-hand turn. Right, now, once again, I'm going to provide you with some code to help you answer this question. Answering this question is sort of beyond the scope of what we're doing here, so I'm just going to directly give you the code necessary to do this. All right, so here is a method in Java. It's a static method that you can use to answer this question. Given any 3 points, P, Q, and R, this will answer the question, as you pass Q on your way to R, are you going to be making a right-hand turn? And if you are making a right-hand turn, this method will return true. Right, and the method has all the logic necessary to answer that question. Again, I won't describe in any detail exactly how this logic actually works, because that's a little bit complicated. It would take us a little bit too far afield from what we're doing. So I'm just going to straight up give you the code to answer this question, and with the guarantee that this will always answer the question correctly. for any group of 3 points that we're working with. This will allow you to distinguish whether the turn as you pass Q is a right-hand turn or a left-hand turn. Okay, so those are two of the sort of foundational concepts that we're going to need to make the lab exercise actually work. What I'm going to do for you next is I'm going to describe to you the actual algorithm that we're going to be using to build our list of boundary points. And as we'll see, the algorithm is going to make use of both of this polar angle concept and also of this left turn, right turn distinction that we're seeing here. All right, so let me pull up a second set of notes here. This set of notes here that will show you an illustration of how this algorithm actually works. Okay, so what we're going to see here in the illustration is a set of points in the plane and a series of pictures that are going to take us step by step through the process of constructing the boundary curve that we're looking for. Right now, first, before I dive into the specifics of how this algorithm works, let me make one remark about what the final result is supposed to look like. Right, the very last picture in the sequence here shows the successful construction of the boundary curve. Right, and again, what the boundary curve does is it passes through some of the points in the collection of points, and it basically wraps around all of the other points that are available in the original set of points. Okay, now an important observation about the kind of boundary curves that you'll end up with is it turns out that if you start at the bottom of the boundary curve and walk around the boundary curve in a counterclockwise direction, one thing that these boundary curves will always do is at every point you pass, you will always find yourself making left-hand turns. Right? So if you walk all the way around the boundary curve from the beginning back around to the beginning, at every single point that you pass, you're going to find yourself making a left-hand turn. Right? In fact, that is a very important distinguishing characteristic of the boundary curves that we're looking for. We're looking for curves that wrap all the way around the points. And furthermore, these are curves where every turn you make is going to be a left-hand turn. Right? And that observation about always making left-hand turns is one of the keys to understanding how this algorithm actually works and how it builds the boundary curve. All right, so let's now rewind back to the beginning of the process and explain how the curve building process works. All right, the first step in the curve building process is we have to take our collection of points, which are going to be scattered around the plane more or less at random. And the first thing we have to do is we have to identify one special point that we're going to call the reference point. And the way that you locate the reference point is you look at the coordinates of all the points that you have, and you go looking for the point that has the smallest possible y value. Right? So in the picture here, the point that's labeled P0, this is going to play the role of the reference point, and it's chosen for that role because it has the lowest y value of any of the available points. That's why that particular point gets chosen. Right, now, once you have designated a reference point, the next thing you can do is you can start computing polar angles. What you can do is you can use this as a reference point, and you can go to any other point in the collection and then measure the angle between the x-axis and that other point, and that assigns an angle to each one of the other points in the set. All right, and then finally, the last thing you do is once you've assigned an angle to every other point, you then go into your collection of points and you sort them based on those angles. And the points end up being sorted in order from lowest angle up to highest angle. And that's the ordering that you see being applied to the points here. All right, so the remaining points are labeled P1 through P12. And the order of the labeling is determined by the angles. They go from lowest angle systematically up through the highest angle, and that's how you organize the remaining points. Okay, now, again, since this is a fairly complex algorithm, let me again invite you that if at any point along the way, if you have a question about anything you're doing, please feel free to interrupt me and ask your question as we go along here. Okay, so this is the first stage of the algorithm, locating the reference point, computing angles for all of the other points, and then using those angles to sort the points into order by angle. Right now, once we've done that preliminary setup work, we're then ready to actually start the work of building the boundary curve. Right now, to construct the boundary curve, what we're going to be doing is we're going to be working with two separate lists. One list is going to be the list of all of the other points. This is basically the points P1 through P12. And the second list we're going to work with is a collection of boundary points that we're going to be collecting as we go along. All right, and at the beginning of the process, the first 3 points that we put onto our boundary list are the reference point and the first 2 points in the set of other points. All right, those 3 points always form the starting set for our boundary list. All right, and then the rest of the points, points P3 through the last point, they're going to be available for us in the other list, and we're going to work our way systematically through the other points. And along the way, what we're going to be doing is we're going to be making decisions about which points we would like to keep in our boundary set and which points we would like to throw away. Right, and to do that, we're going to do a series of rounds, and the pictures here basically illustrates what happens in each of the rounds that we're going to do. And as we work our way through the pictures one by one, what you're going to start to see happen is you're going to start to see the boundary curve being formed and adjusted as we go along to get the right result that we're looking for. Okay, now here's how these rounds are going to work. In each of these rounds, what we're going to do is we're going to go to the next available point in our list of points, and we're going to try to connect that point into our boundary curve. Right now, in some cases, if you simply added that point to the boundary curve, that would cause a problem in your boundary curve. And let me explain why, since P3 is the next available point, why as soon as we try to add it to our boundary curve, that would cause a problem. All right, the problem that would cause is that if you try to simply add P3 to your list of boundary points, that would then cause a problem for the boundary. Specifically, the problem it would cause is that as you round the curve going past P2 toward P3, you would find yourself suddenly making a right-hand turn. Okay, now right-hand turns are things that we have to avoid in this scenario because, again, in the final result, we want to end up with a curve that has only left-hand turns. Right, so whenever we find ourselves in a situation where we're about to create a right-hand turn, we're going to have to do something to avoid that situation. All right, and the thing that we're going to do is that whenever we find ourselves passing a point and making a right-hand turn as we pass that point, we're going to say, oh, there must be something wrong with that point. Let's simply get rid of it. All right, so what we're going to do in response to the fact that we would be making a right-hand turn as we pass P2 is we're simply going to remove P2 from our boundary list. We're going to take it off the boundary list and throw it away and simply discard it. Right now, after you throw point P2 away and then try to add P3 to the list, at that point, everything looks good because now you have 3 points in the boundary set. And in particular, as you pass this middle point, you'll find yourself making a left-hand turn, which is good. That's something we're looking for. Okay, now, from this point forward, each round involves the same set of ideas. And each round, what we're going to do is we're going to go to the next available point. We're going to try to add it to our boundary set. And as we're adding it to our boundary set, we'll be careful to make sure that we don't accidentally create a right-hand turn. All right, so in the next round, we're going to add P4. And you'll notice as you add P4 to your boundary set, everything still looks good. Because now as you pass P1, there's a left-hand turn. As you pass P3, there's a left-hand turn. And everything looks good at this point, and that means nobody needs to be thrown away. Right, now on the next round, we're going to try to add point P5. And as you'll see from the picture here, if you do try to add P5 directly to the boundary set, that's going to cause a problem for P4. Because at P4, you're going to find yourself making a right-hand turn as you go past P4. So as soon as we discover that, we say, oh, we need to remove P4 from the boundary set. And then as soon as P4 is gone, you're good again, because now as you pass P3 on your way to P5, you're making a left-hand turn, and that's good. All right, next we add P6. P6 is not a problem because as we pass P5, we will be making a left-hand turn. Then we add P7, and again, P7 is not a problem because as you're passing P6 on your way to P7, that's also a left-hand turn. All right, so at the end of this sequence of operations, we've got ourselves the beginning of a boundary. And again, every one of these boundary points is making a left-hand turn, and that's all exactly what we want. All right, next we'll try to add P8. Again, the same thing's going to happen with P8. When you add P8, that's fine because as you're passing P7, that's a left-hand turn, and that's good. Okay, now in the next picture, what we would try to do is we would try to add P9. As soon as we try to do that, that causes a problem for P8 because you would be making a right-hand turn at P8. So that forces us to throw P8 away. All right, so then we try again with P7. All right, well, P7 is also a problem because as you're passing P7 on your way to P9, that's also going to be a right-hand turn. All right, so we have, in this case, we have to throw away a couple of points. We have to throw away this one and this one, so that finally we end up with this stretch from P6 to P9, and that's okay because now, once again, all the turns are left-hand turns. All right, and then in the next round, we would try to add P10, which would cause trouble for P9. That would cause us to throw away P9. And once you throw away P9, you also have trouble with P6. That's also a right-hand turn. That gets thrown away. And then also you're going to have trouble with P5 because as you're passing P5 heading toward P10, that's also a right-hand turn. That causes you to throw away P5. And finally, after you throw away P9, P6, and P5, you're good. Now the curve going around P3 toward P10 is okay. All right, and so on and so forth. We basically continue that process, and on each round adding one new point to the boundary and sometimes throwing away earlier points that were in the boundary until we make it all the way back around to the origin point, and at that point the algorithm is concluded and we have constructed the boundary curve that we're looking for. All right, and since we were very careful at every step along the way to throw away any point that would cause a right-hand turn, that guarantees that the list of points we end up with at the end will have only left-hand turns in them, and that's exactly what we're looking for in the boundary curve, right? And that concludes the algorithm that we're doing here. Okay, so once again, this is moderately complex. Let's have an opportunity for questions here. Would anybody like to ask any questions about how the process of adding points and throwing away points works?
So how would you go about throwing away the points that, like, it's like a situation once you add P10 where you have to like throw away multiple of them?
As you can probably guess, that's going to involve a loop. So in the logic that we're going to be writing, there's going to have to be a loop that basically tries multiple times to see if we've got right-hand turns. And as long as it keeps seeing right-hand turns, it will keep throwing away points. Yeah, so that's the key to doing that successfully, is that we're going to have to build a loop into our algorithm that allows us to keep throwing away points, as many points as necessary, until we get to something that works. All right, any other questions about the algorithm at this point? Okay, now the next thing I'd like to say is that this is all complicated, sufficiently complicated, that to help you out, I have provided some details to help you in the lab materials that you're going to be working with. All right, so first of all, in the lab materials for today's lab, I also have reiterated some of the things that I've just shown you here on the slides and in the notes. And one further thing that I've done that will be a key piece of material that you'll need to refer to as you're doing the lab is here I've written out in words all the key steps in the algorithm. All right, so this is probably the most important piece of information in the lab materials that I've provided. This basically gives you a step-by-step roadmap through the steps in the algorithm that you're going to be implementing. Right, so you'll be able to refer to this. This will basically tell you in words what you need to do in each key step of the algorithm, and you can use this as a roadmap for writing the code that needs to be written for the lab exercise. Okay, so at this point, you've got an awful lot of information to look at. I want to end with one final comment about an important step that's going on in this lab exercise, and that is step 3 in the outline here. Right? Because in step 3 in the outline, what's going to happen is after we found the reference point, you're going to write a loop that goes through and computes the polar angle for every one of the other points relative to the reference point. And then once you have polar angles assigned to each one of the points, what you need to do next is you need to sort those points by those polar angles. Right, now I want to say something explicitly about that, because although this is something that we've talked about in an earlier lecture, you may have forgotten the details of how this works. So let me go back and remind you a little bit about how you can put a collection of points in a list and then sort that list based on some criterion. That's going to be a key step in the algorithm. Right, so in the lecture notes for today's lecture, I've provided you with some further information about sorting the list of objects. And there's 2 specific things that I want to draw your attention to. One is that there is a section in the textbook that covers this topic, how to actually set up a collection of points so you can sort them. That section in the textbook is section 13.6. And one of the things that I'm going to recommend that you do in between today's lecture and the lab exercise is that you go and read that section in the textbook, because that will give you further information on how to prepare a collection of objects so they can be sorted, and then how you can go ahead and sort those objects. And then a second thing for you to look at is that this is actually a topic that I covered in an earlier lecture, and there's a link here from today's lecture notes to that earlier lecture, and there's a section in that earlier lecture where I talk about how to sort a bunch of objects. So you might want to go back and review that section from the earlier lecture notes to review how we did that in that earlier lecture. This again will give you some more of the necessary background information for this very important step of taking your collection of points and then sorting them based on their polar angles. That's going to be a key step in the algorithm, and you'll need to read this background material to see how to actually carry out that step. Okay, so that's all that I have for you today. And since we don't have enough time to start anything new, we're just going to end a little bit early today. So before we go, here's one last opportunity for you all to ask any questions about anything related to the lab exercise. If there's anything that I haven't covered in detail and you'd like to see me go back and talk about some more, I'm welcome to answer questions at this point. Okay, now one final remark about the lab this week. Last week, as sort of an experiment, we tried doing the lab working with partners. And for the lab this week, I will give you the option of doing that. So if you would like to work with a partner for this week's lab exercise, I'll give you the opportunity to do that. If you instead prefer to work on the lab exercise yourself, you certainly will also be able to have that option as well. Right, and what we'll be doing at the beginning of each lab session this week is I'll be organizing everybody so that those of you who want to work as partners, I'll be organizing you into partners. And for those of you who want to work by yourselves, I'll give you the opportunity to do that. And we'll do all of that organizational setup at the very beginning of the lab exercise in each lab session this week. All right, so until then, I'll see some of you in tomorrow's lab sessions, and I'll see everybody back again on Wednesday for a lecture. All right, so long until then.
Thank you.
You're welcome.